the title suggests, I'm going to tell you a little bit about homotopy coherent cyclic operads, or as much as I really can, given the time constraints. So I can't really go very deep, but I can give you a taste. Right, so I'll tell you about cyclic operads first, give you an overview, and then, like anyone who knows higher category theory, I'm going to need some graphical category, similar to simplicial sets. So I'll be talking about cyclic dendroidal sets, and there'll be a nerve theorem in there, just for good measure. Then we're going to get a bit homotopical. I'll put a microphone on. All right. So I'll give you an imprecise definition of a cyclic operad, because the full definition is several pages and it looks gross. But what I want you to pay attention to here is that we're starting off with a color set, C, which is equipped with a free involution up here. So most definitions you might have seen, if you've seen cyclic operads before, might have a set of colors, if they're colored cyclic operads, but the involution is not necessarily standard. This is introduced by Drummond, Cole, and Hackney. So a C-colored cyclic operad is just a bunch of sets indexed by sequences of colors in our color set. We've got a symmetric group action permuting these guys here. And most importantly, we've got these composition maps. So when we have one of these guys indexed by this list C and this list D, if CI is equal to DJ involution applied, then we can compose. And this is shorthand for it goes C1 up to CI minus 1, then D1 up to DJ minus 1, and then DN back round again and through the C's again. Anyway, it doesn't really matter what that actually is. So we've got these products, and the important thing is that unlike operads, which are directed, so we have inputs and outputs, these guys have no idea of direction. They're just these kind of star-like things that glue together. So there's these equivariance, associativity, and unit axioms, which instead of listing, you can kind of get by looking at this prototypical example, which is pick some color set C, and we'll let tree C be unrooted trees with the legs, so these outer edges here, labeled by elements of this color set. And the symmetric group will just act by permuting labels around. And composition is just grafting the trees. So we can see here, if we graft, say, the third guy to the fourth guy, we've got this compatibility here. They'll glue on like this. And the units are just given by the naked edge that doesn't have any vertex. Now, this is sort of more than a prototype example. This is, if you want to be formal about it, basically, it's a description of the monad whose algebras are these cyclic operads. So if you remember Kurt's talk yesterday, Kurt Chandan's talk yesterday, he had this monad for his guys. It's a similar situation here. Okay, well, maybe a more important example is the cyclic operad generated by a tree, so an unrooted tree. So we're going to fix a tree, and we're going to be working with trees with half edges. So in the data describing our tree, we have a set of vertices, and then instead of edges between vertices, we have, well, they're kind of divided into two bits, these half edges. There's an involution on each edge that swaps which of the two it is around. They're also called arcs in the literature. So we're going to write omega sic T for the cyclic operad generated by T. And it's going to be, so it's a colored cyclic operad, and the colors are the half edges of T. And the involution is just going to, as I said, swap the half edges around that constitute the single edge. And our operations are generated under grafting by vertex neighborhoods of T. So this means that OSIC of A1 up to AN, it's either a one-point set if there's a subtree whose legs are that list of colors, or it's empty otherwise. So just to emphasize this use of half edges is exactly why we have the involution in the definition here, which is not historically standard. This also gets us the nice fact that this cyclic operad generated by a tree is actually finite. Whereas if we don't have the involution present, it's pretty easy to cook up an example where you get a generated operad out of a tree and it ends up having infinitely many higher operations. Because you can just keep gluing, say, a vertex with two edges, you can just keep gluing that end to end forever, which is not allowed when we have this involutive structure present, which is nice. Also, given the audience I'm speaking to, I thought I'd mention that whereas colored cyclic operads traditionally are a simultaneous generalization of operads and dagger categories, with this definition, they're a simultaneous generalization of star autonomous categories and operads. So they do have more expected pleasant formal properties. All right, so now we want to get a bit more homotopy coherent. So as we have to always do, we have to introduce a graphical category. So we call this omega sic. This notation goes back to Mordyke and Weiss. They chose omega for the dendroidal category for operads, so that's what we're going to do. And it's going to be a category of unrooted trees with legs. That means that there's always at least one external edge. And we're keeping track of the data of half edges. And the morphisms are just going to be the morphisms of operads between the cyclic operads generated by the given trees. You can define this intrinsically as well. It's just a bit longer, whereas this is a pithy definition. Now, a cyclic dendroidal set then is going to be a pre-sheaf on this graphical category. So this is just a step up, a generalization of simplicial sets. So this particular graphical category was introduced by Hackney, Robertson, and Yao in the context of studying a graphical category for modular operads. And it's heavily motivated by the work of Mordyke, Weiss, and Szyszewski in their dendroidal sets. Just note, we're going to representable pre-sheaves are going to be given by this guy here. And note that by definition, the sending T to the cyclic operator generated by it is now a fully faithful functor, which is actually not possible without the half edges, precisely because of the hand wavy example I gave before of being able to get an infinite operad out of a tiny little tree. So this is nice. All right, so morphisms, just like in simplicial sets, we get this decomposition into a small set of morphisms, namely isomorphisms, so non-planar isomorphisms of trees, and what's called inner face maps, outer face maps, and degeneracies. So inner faces just blow up a vertex to add an extra edge. Outer faces just include a guy with an extra vertex, and degeneracies kill off a bivalent vertex. So for the purpose of this talk, we care most about the first case, but we're blowing up to get an extra edge. And I'll tell you about that why in a moment. Right, so this is a bit of a technical slides. So let's take a coface map. So let's recall that's blowing up a single little edge, vertex to get an edge. A face of T is just the image of on the representables of a coface map. And the horn, for given a coface map, is just the union over all other cofaces that aren't that one. So then we just say a horn if it's a horn for some coface map, and an inner horn if it's a horn for some inner coface map. This is just like horns in the context of simplicial sets, just maybe a little bit more difficult to draw, get a geometric intuition for. The point of this is we're going to say a cyclic dendroidal set is in a Kahn if every diagram of this form, the horn on top, has a lift called a horn filler. So this is exactly reminiscent of the Kahn condition for simplicial sets. And we say X is strict in a Kahn if every horn filler is unique. All right, so what I'm going to say next won't be too surprising. So in order to compare cyclic operads in these dendroidal sets, we'd better introduce some way of taking a cyclic operad and getting a dendroidal set. This is the cyclic dendroidal nerve, defined like this. In particular, it sends the cyclic operad generated by a tree to a representable. So it factors the Enoda embedding. This actually is super easy to prove, but is actually extremely useful Among other things, it tells us that cyclic operads have a decomposition in terms of these three guys in terms of trees, much like how pre-sheaves have a decomposition in terms of representables. It turns out to be very nice. And our first theorem is that a nerve theorem stating that every cyclic dendroidal nerve is fully faithful. So cyclic dendroidal sets are a lossless representation of cyclic operads. And the essential image is precisely the strict inner Kahn cyclic dendroidal sets. I'm actually underselling this theorem a bit because there is also a Siegel component, but I just didn't have time to describe the Siegel condition. But let's go with this one for now. So this is inspired by very similar results by Mordek and Weiss in the context of operads and dendroidal sets. Hackney, Robertson, and Yao have a nerve theorem in the very, very similar case where we don't have the involution. And obviously, well, historically, these sorts of nerves go back to growth and deconceal for categories and simplicial sets. So there's a rich history of this type of thing. Right, so since we have these, cyclic dendroidal sets and we can realize operads inside them using this inner Kahn condition, it makes sense to loosen up that inner Kahn condition, which gives uniqueness of composition by the strictness of the lift, to get non-unique lifts and therefore have an infinity guy. So for us, a cyclic infinity operad is a cyclic dendroidal set which satisfies the weak inner Kahn condition. So that means every inner horn has a lift, but not necessarily unique. So obviously, this idea goes back to that of quasi-categories as introduced by Boardman and Boat. All right, so since I'm talking infinity, I need to take a little digression into model categories, but it will pay off. Namely, I've told you that we've got this guy called cyclic infinity operads, but I haven't really told you that any exist. And actually, I can't write down an example now. I'm working on one at the moment explicitly, but right now there's not really an explicit example of something that is a cyclic infinity operad and not just a cyclic operad. But we'll get there. So one other model for an infinityified version of cyclic operads is just to consider cyclic operads in the category of simplicial sets. So same definitions go through as we had in the initial one for sets, just there's simplicial sets everywhere. And there's a model structure introduced by Drummond, Cole, and Hackney, which is transferred from the model structure on simplicial operads, which is due to both Berger, Mordek, and Robertson independently. Namely, so a morphism is a weak equivalence if it's locally a weak equivalence. So for every profile C, every list of colors, that space of operations becomes a weak equivalence of spaces, and likewise for fibrations. So it's kind of and also, sorry, I should say, and it's a weak equivalence of underlying categories or a fibration of underlying categories respectively, where I'm being a bit hand wavy about what I mean by underlying category, but if we take a cyclic operad, we can forget the cyclic structure and it has an underlying operad. Now, the underlying category of an operad is you just forget all the higher operations above having two colors, and those become your hom sets. And the objects of that category is your color set. Anyway, it's not really the focus. All right, so we have this model structure on simplicial cyclic operads. Very good. And we want to compare this a bit to our cyclic dendroidal sets. So whereas before we had this nerve going from operads to cyclic dendroidal sets, we want something that's a bit more homotopy-ish, a bit thicker, going from simplicial cyclic operads. So to do that, we have to introduce the cyclic W construction. So what I'm going to show you here is a kind of a low-tech version. If you're interested, you can speak to me. Johnson and Yao have some super high-tech stuff in an upcoming book. So to fix some terminology, let's say a C-colored tree is just a tree together with an involutive function labeling all the half edges by a color C. And a P-labeled tree, given a C-colored cyclic operad, is a C-colored tree where on top of that, all the vertices are labeled by an operation of P. So you think of this, an operation P, the vertex, say in XY colors, say C1, C2, C3, and then neighboring vertices have to match for that operation. Finally, a thickened p-labeled tree, this is not standard terminology, I just thought I'd use it, is a p-labeled tree together with a choice of length on each internal edge. I should have included a picture here, but I didn't. So think of this as you've got vertices all labeled by operations in P, and now the edges have some length between 0 and 1. Well, the cyclic W construction is this horrible looking guy. What this is it's the elements of this are p-labeled trees. So this is what this set here represents. So it's a length for each internal edge, an operation for each vertex. This coproduct is over all trees whose legs are colored by this profile of colors C. And we have this equivalence relation where we say that if the edge is labeled by 0, just contract it, and the two adjacent operations on vertices are composed. Bivalent vertices labeled by the unit are just removed, and the resulting new edge is just the max length of the other two edges. And this is actually a cyclic operad under grafting, where the new edge created by grafting two legs together, we just give it length 1. So as I said, this works for cyclic and even modular operads in any closed monoidal category. I think it works for generalized props is what they have, Johnson and Yao have in their book. It's a definition in terms of a coend on an appropriate category. So if there's any category theorists out here that want to know more, I'm happy to talk about that. Okay, so what's the point of this guy? Well, it's going to be the stand-in for our thickened nerve for what the cyclic operator generated by a tree was for our initial cyclic dendroidal nerve. So in particular, we have a homotopy coherent nerve given by, evaluated on a tree T, it's just the morphisms of cyclic operads from the W construction on the free cyclic operad generated by T into P. So importantly, unlike the cyclic dendroidal nerve, the homotopy coherent nerve is not going to land in strict inner Kahn land. This is basically because if we have, say, two trees and we want to graft them, so this is similar to composing two operations. Well, when we graft them, we get an edge of length 1, but an ambient tree that's sitting around there that has exactly the same shape could have a whole list of different edge lengths ranging from 0 to 1. So when we fill this in a horn, there's a whole sort of plethora of options for horn fillers. There's a whole interval of options. So we can't expect this to actually be strict. But the main theorem of my thesis states that when P is a fibrant simplicial operator simplicial sets, then the homotopy coherent nerve is a cyclic infinity operator. So this gives us a wealth of new examples of cyclic infinity operads. So if you pick your favorite simplicial cyclic operad, if it's sort of combinatorial and detailed enough, you could probably get a nice, straightforward description of a cyclic infinity operad, which is nice. All right, so I want to sketch the proof in the last 5 minutes of my talk. And I kind of thought the whole purpose of this talk was sort of to advertise this method of proof as well. So this theorem exists for the context of operads and the homotopy coherent nerve there, and also for simplicial categories. And both of those cases use quite different proofs, but they kind of all boil down to some fairly just nitpicky simplicial homotopy theory. So you have to really go down to the bones to do the proof. Whereas this proof I have here really just uses pleasant kind of naturality properties of the W construction. So it gives sort of hope of generalizing this type of result to more other types of generalized operads, which I think is pretty cool. So we're going to write usic for this forgetful functor, going from cyclic operads to operads, and fsic for its left adjoint, so it's the free functor. And we're going to have this functor of graphical categories going from the dendroidal category of Mordich-Weiss to our cyclic dendroidal category, which just takes a rooted tree and forgets its root. Nothing fancy going on here. And this just by standard stuff, induces a adjoint triple between dendroidal sets and cyclic dendroidal sets. So in particular, this middle guy is just restriction along this functor F. Now, if we have a fibrant cyclic operad in superficial sets, then just by the definition of the model category, the way we got it by transfer, that forces USIC to be a right Coulomb functor. So USIC of P is also now fibrant in superficial operads. So by the homotopy coherent nerve theorem of Mordijk bias, the homotopy coherent nerve of the underlying operad of P is an infinity operad. I probably should have had a diagram here, but we've kind of gone up one side of a diagram. Okay, now next is a relatively easy fact that F star of a cyclic dendroidal set is an infinity operad if and only if X is a cyclic infinity operad. So imagining the diagram that I should have put in, without forgetful functor from operads, cyclic operads to operads, homotopy coherent nerve, cyclic homotopy coherent nerve, and this F star going up the left-hand side. So all that remains to check in order to prove our theorem is that this diagram is actually commutative, right? So that F star of the cyclic homotopy coherent nerve is the operadic homotopy coherent nerve of USIC of P. And this, it turns out, well, let's look at how this goes. So this first step is just literally the definition, then just adjoint. Then the first non-trivial input is this step here, which is the nice fact that the free cyclic operad generated by the W construction on the operad generated by a tree T, rooted tree, is in fact the cyclic W construction on the free cyclic operad generated by this guy. So if you draw a picture of what's going on here, namely that the free, so the W construction is like close to being a free construction. So kind of saying free commutes with free. You can convince yourself that this is true by drawing a couple of pictures. The proof more or less is that picture description just using the universal property of coens. Next is this fact that the free cyclic operad on the operad generated by a tree is just the operad generated by that tree once we forget the root. And then finally, we're home, just by definition. So it's this naturality property here, which is really the only non-trivial step in lifting this homotopy coherent nerve theorem from operads to cyclic operads. So if we could establish similar theorems and comparisons for modular operads, dioperads, you name it, then there should not be many obstructions to lifting this theorem to those contexts. Right, so just some perspectives. So there's a conjectural model structure on cyclic dendroidal sets, which should be very similar to the Joyal model structure on superficial sets, or the Mordijk-Zasinski model structure on dendroidal sets. Namely, its fibrant objects are the cyclic infinity operads, and it should be Coulomb equivalent to the Drummond-Collin-Hackney model structure on superficial cyclic operads, just how the Joyal model structure is Coulomb equivalent to the Bergner model structure on superficial categories. So obviously, yeah, this is consistent with everything else. And this main theorem is at least a piece of evidence, right? If that theorem wasn't true, that would be game over. But that says at least that the homotopy coherent nerve looks like a right Coulomb functor on this so far non-existent model structure. I have some ideas on how to do this, namely by transferring from dendroidal sets, but I'll just keep running into sort of dead ends. So if anyone has any ideas, talk to me and we can write a paper. Thanks.
Okay, thank you, Patrick. Any questions?
Your hand-wavy description on why it's evolution. Do you mind going into more details about?
Yeah, sure. Camera can see me, so I can do this. So let's just take this tree here. And
No, could you use these guys because I don't have this here.
all right. So let's make sure I'm seeing